Hi there, welcome to a video on calculating sensible heat flux using surface renewal measurements. Here are some contact details. There are a few surface renewal methods. However, they all involve relatively high frequency measurements, normally about 10 Hertz, of air temperature using an unshielded fine wire thermocouple. From these relatively high frequency measurements, every 30 minutes, 3 air temperature structure functions are determined. The second order air temperature structure function, the third order, and the fifth order. These measurements are then imported into a spreadsheet and then calculations done to obtain the surface renewal sensible heat flux. In this particular case, VBA is used to do the calculations. VBA is a useful tool for doing sophisticated calculations behind the scene of the cell user interface. To see the VBA code, we press on a laptop Alt function F11. I've called the function SR and the user specifies various options. I won't go through the VBA code, but we will, however, look at how to apply this function in Excel in a particular cell. The spreadsheet uses custom views. To invoke custom views, we press Alt V, and those are the different custom views that I've created. If we want to look at just some of the references involving surface renewal, double click on references. If we want to see some of the theory, Alt V, theory. That's a fine wire thermocouple which is used for the relatively high frequency 10 Hertz air temperature measurements. The three equations that are important are this one to calculate the sensible heat flux in terms of the ramp amplitude in degrees Celsius, the ramp period in seconds. This is the Van Atta equation for the ramp amplitude. It's a depressed cubic polynomial, depressed because there's no second order, and there are different ways of solving it. And then there's this equation here for determining the ramp period in seconds, and then the sensible heat flux we've mentioned already. There are probably 4 ways of determining the ramp amplitude in degrees Celsius. There's the full Van Atta approach, which we won't use in this spreadsheet, except we'll use the Van Atta equation. The other way is to make A the subject in the formula, the A and A cubed, to obtain this relationship, and then use an iterative approach to obtain that root. A third way is to use the Newton-Raphson method for solving polynomials. This is the depressed polynomial, and this is the one that will be solved in the VBA code using the Newton-Raphson method. How does the Newton-Raphson method work? Well, a guess is made for the root of the polynomial, say 1. The function is evaluated at 1, and a tangent line is drawn at that function value. That tangent line has an x-intercept. That's used as the first guess of the root. For that first guess, the function is re-evaluated and another tangent is drawn for the function at that first guess and an x-intercept obtained. That is the second guess of the root, that x-intercept. Another tangent is drawn yielding another x-intercept and that's the third guess. And so the process continues until convergence. Convergence occurs within a certain precision set by the user. That's the Newton-Raphson approach. The disadvantage of the approach is when the first derivative of the function happens to be 0 at a particular guess or subsequent evaluation of the root. Then the root cannot be determined. Alt VV. Let's look at the SR VBA function. To evaluate the function, we type equals SR bracket and firstly an option. And that option is 0 for the ramp amplitude in degrees Celsius, 1 for the ramp period in seconds, and 2 for the sensible heat flux in watts per square meter. The user then indicates the time step of the output data from the data logger. Usually that's 30 minutes, but we indicate 1800 in seconds. The user indicates the measurement height of the surface renewal thermocouple. The delay that's used in the data logger program for that particular thermocouple. Delays are typically 0.4 or 0.6 of a second. Then the three air temperature structure functions, the second order, third order, and fifth order. Then the seed that is used. Now, the user can indicate a seed of 1. And if the third order air temperature structure function is negative, that will result in a positive amplitude. So it makes sense to use a positive seed, and that namely is 1. However, if from the input data VBA encounters a positive third order air temperature structure function, it knows that the amplitude is going to be negative. So it forces the seed to be negative, otherwise the solution will never be found. And then we indicate the precision of convergence, typically a whole bunch of zeros and 1. Here's the function evaluated then for option 2, namely sensible heat flux in watts per square meter. 1800 is the time step of the data, the 30 minutes. 3.7, the measurement height. 0.4, the delay in the measurements from the data logger program. The second order, third order, and fifth order air temperature structure function from the data logger input data. The seed, typically 1, and then the precision of the convergence. So we end up with 42.02 watts per square meter. Alt VV again. Let's look at the input data. There's the date timestamp from which we can compute the day of year using normal Excel functions. The data logger gives us as well the air temperature structure function, the second order for thermocouple 1, lag 1, thermocouple 1, lag 1, third order, thermocouple 1, lag 1, fifth order. Then it repeats it for the second lag for the same thermocouple, repeats it for the second thermocouple for lag 1, the same second thermocouple for lag 2, continues for thermocouple 3 and thermocouple 4. This version of the spreadsheet allows 4 thermocouples, 2 lags per thermocouple, and the 3 air temperature structure functions, second, third, and fifth. And it goes every half hour from the top to the bottom of the data, the input data. Alt VV. Let's look at the SR VBA output data. For this column here, it's the ramp amplitude. There's the date timestamp. There's the day of year. The amplitude in degrees Celsius, the ramp amplitude, and we specify option 0 equals SR bracket 0, and then the difference in the first two date stamps in days times 24 times 60 times 60 to get it to seconds. That will give 1800. AI 78 is the first thermocouple height for that surface renewal thermocouple. AI 79 is the delay from the datalogger program for those measurements, and then the second order, the third order, and the fifth order air temperature structure function. 1 is that seed, and then the precision that we specify. Press enter and it will calculate. Copy that to those two cells, change 0 to 1 to get it to be the ramp period in seconds, change the 1 to 2 to get the sensible heat flux in watts per square meter. Copy those three to these three cells, copy those three to these three cells, and all the way across, and the column numbers should automatically update. I'm going to use this set of cells as a template, copy it down to the first date timestamp of the output for the output data, and then double click down to fill the rest. Calculations aren't automatically updated because I've put off the calculation update. To do the calculations, it's function F9, and in the twinkling of an eye it will update the calculations. So that's the ramp amplitude in degrees Celsius, the ramp period in seconds, the sensible heat flux in watts per square meter for the first thermocouple, for the first measurement height, for the first delay. And so it continues for the second thermocouple for the second delay, first thermocouple for second delay, and then the second thermocouple, first delay, second thermocouple, second delay, and so on. The disadvantage is that when the derivative evaluates itself to be 0 in the denominator, I've then forced the VBA code to give an output of 9999. Otherwise, it'll calculate the sensible heat flux very efficiently. I hope you've enjoyed this video on determining sensible heat flux using surface renewal measurements. Thank you. Cheers.